Hello everyone. Today we're going to talk about branch and bound approach to solve problems. Before we learned about backtracking. So as you remember, for solving the knapsack problem 01 knapsack problem, we were creating a tree, okay, although not actually, but like the logic of the backtracking was to create a tree. So here we had an empty node, we had the empty bag at first. Then we are including or not including an item in the bag. So at the first level, we had including the first item that was ordered based on the ratio of the value to the weight. Then we're adding the second item or not adding the second item. Again here adding or not adding. And the third level we have including the third item, okay, based on again the ratio of the value to rate or not including that. Also, as you remember, the backtracking was using a depth first approach. So it was meaning that first we are starting with the root, okay, we're going here to the first node, then we were saying about including the second one, then going to see that if we can include the third one or not. And any times that we were finding that we cannot go further, okay, and for example the case that the node was not promising, okay, so when the node was not promising, then we were going back, okay, we were backtracking and we were trying another node, but still our approach was a depth first search. Now today we're gonna see that how we can improve that, okay, using a branch and bound approach. So instead of using a depth first, we are gonna use the breadth first search to prune and find the best possible solution. So let's do this example. Let's do one example and see that how this approach works. Okay, now let's see how what the branch and bound means. So assume that we have these four items, P1 to P4, that are the values, and also the weight 1 to weight 4 that are the weight for four items that we have. And the goal is, as the 01 knapsack problem says, to try to pick as much as item we can that has the maximum values together. So let's say that we are creating a tree for this problem. And the first level that is going to be level I, or is going to be level I equal to 0, so that L stands for level. And let's say that we also have another level K. And assume that we are level I, and we are going to see that what's going to be the maximum bound that we can obtain up to that K. And that K is the level that whose weight, okay, would bring the weight above W that we have. So if we're also to write here, so the maximum weight that we can take is 16. So that K is the level that whose weight, okay, would bring the weight above W. Let's see in this example when we are at level I equal to 0, what's going to be the K. So if we sort the numbers like the ratio of the values to the weight, you will see that P1, okay, has the higher ratio. Then the P4 is the P4 has the lowest ratio. So together we're gonna like to have this formula that says about the bound. First, we need to define the K. So if you look at the weight, the maximum is 16. So 2 plus 5 is 7, and 7 plus 10, okay, is equal to 17. Okay, so the maximum, so the K is equal to 3 in this case, because after 2 and 5 and 10 and becomes 17, that is greater than 16. So K will be 3. Now let's define some formula to see that what's going to be the value for bound. First of all, we are defining the total weight. So I'm going to just write the total W. That is the weight that we obtained so far, that the weight that again that we had so far, plus the summation of the weight. Let's define some index j from I plus 1 up to k minus 1 of weight at index j. And why we're saying that j should be start I plus 1, because as we said, we had the weight up to the index I before, so that's why we're starting from I plus 1 and up to the k minus 1, because as we said, k is the level that whose weight going to be more than like together going to be more than the total weight that we need. So that's why we are going to like to have one index before that. So is up to k equal to 2 here, j equal to 2. So let's see in this example that what's going to be the total W when we have k equal to 3 and I is equal to 0. So we are going to see that what's going to be the maximum bound, okay, at the first level that we have, that we haven't had anything yet. So we have empty bag, okay. So here the total W will be equal to 0 at first because we haven't picked anything yet. I is equal to 0. So we will have the sigma of j equal to 1 to k minus 1, that is 2 of wj. That this is equal to w1 plus w2, that is going to be 2 plus 5, going to be 7. So the total weight, okay, will be 7. Now the next formula that we're going to define is the bound, okay. So let's one here, and the bound, okay, is that how much we can gain from like these three is gonna be the profit so far, so I'm gonna call it P, okay, that we had before, plus the sigma of j equal to I plus 1, okay, up to k minus 1 of pj, plus the total weight, okay, the total weight that we had, okay, the total weight that we had before, minus total W that we calculated, multiplied by the ratio of the item k, so pk divided by wk. Okay, so let's change this one because I don't want to like to be confused, to get confused with this W that we have here. So I'm going to rename it to let's call it WE. Okay, so that is the like the number, like the weight that we had up to item I. Now, so the bound says that what's our previous profit up to level I plus what's going to be our profit, okay, or how much we gain by adding items from I plus 1 up to k minus 1 again. The reason that we are not including k because the total weight we're going to be more than like the limitation of the weight. Plus we have like the weight, the total weight minus the total weight that we are calculating so far, and multiplied by the ratio of this item that cannot be included in the final bound. Okay, so if we want to calculate this bound for this example, the previous gain, okay, will be 0, okay, so because we haven't included anything yet, and here we'll have j equal to 1 to 2 of p j plus w that is 16 minus the total w that is 7 multiplied by pk, and k is equal to 3, so it means that item 3, that is going to be 50 divided by 10. So if we add these numbers together, so p1 plus p2 together are going to be 70, plus this is equal to 9 multiplied by 5 going to be 45, okay, 45, and together, let's write it here, is going to be 150. So that's the total bound that we can obtain, okay, from starting here. So it's going to be 150. So that's the maximum that we can obtain. Next, we're going to like to see that how we can again like draw the tree and see that how we can solve this problem.